Hi, in this talk, I'm going to talk about distributed weighted min cut in nearly optimal time. This is joint work with Michal from ETH, Sagnik from KTH, and Danupon, who is affiliated with both KTH and the University of Copenhagen. So in this talk, I'm planning to first go over the model and the problem we are going to discuss. Then I give a brief overview of some previous work, and then discuss the main components of our algorithm. So let us start. Here we will discuss the weighted min cut problem. Given a graph G, a cut is a set of edges whose removal disconnects G. One can also identify a cut with a subset of the vertices S. Since we are considering weighted graphs, a min cut is a cut whose sum of edge weights is minimal. And in the min cut problem, we are tasked with finding a min cut in a given weighted graph G. For example, here, the dashed cut is a min cut. The model we are going to discuss is the distributed congest model of computation, in which we have a network of n nodes. Communication takes place in synchronous rounds, and nodes have unique identifiers. The initial knowledge of each node is only its immediate neighbors and the weights of its incident edges. We have an O of log n bandwidth restriction. That is, in each round, each node can send a message of O of log n bits to each one of its neighbors. We have unbounded local computation inside of each node. And finally, our complexity measure is going to be the number of rounds of communication. So now for previous work. And the first thing that I want to talk about in this aspect is that there was up to this work a very big gap between our understanding of approximate min cut and exact min cut. So let's go over the results chronologically. First, in 2011, came a lower bound of square root of n plus d rounds, where d is the hop diameter of the graph, which is the same as the diameter, and n is the number of vertices. And this was for weighted min cut. But as I've said, we have now a very good understanding of approximate min cut. A couple of years later came nearly tight algorithms computing a 1 plus epsilon approximation for weighted min cut. That is, algorithms that work in O of square root of n plus d time. But when it comes to exact algorithms, the picture is far from being complete. The first breakthrough came in 2019, where the first sublinear algorithm for min cut was developed, but even that was only for simple unweighted graphs, and even additional work that improved upon this upper bound was only able to achieve a complexity of n to the 0.9 in the worst case, again, only in simple unweighted graphs. The state of the art for weighted graphs was still linear time. So when we started this work, we began with the question of whether a weighted sublinear algorithm is even possible. And well, the answer is yes. In this work, we we devise a nearly tight exact min-cut algorithm for weighted graphs in square root of n plus d rounds, which up to polylog factors matches the aforementioned lower bound from 2011. So now I'm going to go over the main points of the algorithm. The high-level approach that we employ is, well, we start with reducing the weighted min-cut problem to the min-2 respecting cut problem, a reduction that was proved by Karger in 1996. And then the crux of our result is an algorithm solving the min-2 respecting cut problem in O of square root of n plus d rounds. So now let me define the min-2 respecting cut problem. We are given a weighted graph G and a spanning tree T of G. We say that a cut E prime 2 respects T if at most two edges of the cut are actually in the tree. Dually, we say that a cut 2 respects T if at most two edges of the tree cross the cut. That is, if we have the edges E and E prime here, they define a 2 respecting cut, which is precisely this one, in which E and E prime are the only two tree edges that cross the cut. And in the min-2 respecting cut problem, we are tasked with finding a two respecting cut of minimum weight with respect, of course, to the original graph. Well, if in the original min-cut problem we had to consider 2 to the power of n cuts, now we only need to consider O of n squared cuts in order to find the minimum cut. Karger showed that an efficient algorithm for min-2 respecting cut implies an efficient algorithm for min-cut, and roughly this reduction finds O of log n trees, spanning trees, such that there is some min-cut S of G that 2 respects one of the trees. This reduction is efficiently computable in congest, namely in square root of n plus d rounds, as was shown in previous work, in which every node knows its incident edges in each tree. So our main result is an algorithm for computing min-2 respecting cut in O of square root of n plus d rounds. Along the way, we prove 2 purely combinatorial lemmas about min-cut structure in a graph and employ a routing trick, on all of which I will discuss later. Let's start with the rather simple case of 1 respecting cut. That is, exactly one tree edge crosses the cut, as we can see in this case with E. And now we say that an edge which is not in the tree, UV, covers E, if E is on the unique tree path between U and V. And we denote by cov E to be the sum of weights of all the graph edges that cover E. Note that in this case, for a single edge, the cover value of E is also the value of the cut defined by E. That is, the cut that E is the only tree edge that crosses it. Previous work has shown that one can compute the cover value of all edges in the graph in square root of n plus d time. So now that leaves us with the more complicated case of two respecting cut. That is, that exactly two edges of the tree cross the cut. Similarly, we define the notion of cov E prime, which is the total weight of graph edges that cover both E and E prime. Note, however, that in this case, it is not true that the cover value of E and E prime is indeed the value of the cut that they define. Because if we look at the cut here, which is defined by E and E prime, note that while the red edges cross the cut, they do not cover both E and E prime, but exactly one of E and E prime. And these are indeed the set of edges who are going to cross the cut. The graph edges that cover exactly one of E and E prime, but not both. As we can see, for example, with this blue edge here that covers both E and E prime, but does not cross the cut. From this observation, we can easily deduce this formula for the cut value defined by E and E prime. So now we would like to solve the two respecting cut problem. Well, a naive attempt will be to go over all pairs of edges and compute their cut value. But of course, this would take way too much time. Our goal then from here on in is to reduce the number of comparisons we have to make. And we start with the work of MN 2020, where they introduced the notions of interesting paths and monotonicity, with which they were able to show that it actually suffices to compare O of n pairs in order to find the min to respecting cut, with which they were able to show improved algorithms for weighted min cut for the sequential, streaming, and cut query settings. But for distributed, this was not enough. And in this work, we generalize and strengthen the notions and properties that they defined in order to devise our algorithm. And we start with interesting paths. So from here on in, we are only going to consider the very simple case that the tree that we are working with in the min to respecting cut problem is a spider graph. That is, we have square root of n legs, each of length square root of n. And let's say that the two edges E and E prime are actually the edges that define the min cut. Well, then of course that the cut, which is defined by E and E prime, has value at most the cover value of E prime, because the cover value of E prime also equals the cut value defined by the edge E prime. By using the formula for cut E prime from 2 slides ago, we can actually deduce that the following must hold, is that the cover value of E and E prime is at least half of the cover value of E. More visually, this means that at least half of the weight that goes from here to the rest of the graph actually goes here. And we now say that an edge E is interested in E prime if this holds. Note here that if E is interested in E prime, it is actually interested in the entire path between E and E prime. Because of course, if half of the weight from here to the rest of the graph goes to here, then of course that the same holds for this. So now what basically they did in MN is they mapped each edge E to a path P in which it is interested in. But is it enough for distributed? And the answer is no, due to congestion. Intuitively, complexity depends on path length and the number of path comparisons. Unfortunately, due to lack of time, I will not be able to go deeper into this problem here. Comparing edges to paths is problematic for distributed. This is why we turn to comparing paths to paths. Why paths? Well, first, paths are topologically simple. We can perform aggregate computations on them, and they are easy to communicate on. But most importantly, we can prove two main purely combinatorial structural lemmas regarding paths, which we use to reduce the number of comparisons we have to make. One is that we are able to bound the number of interesting paths, and the other is a partitioning lemma, which I'm going to discuss later. And again, intuitively, the complexity will ultimately depend on the path length and the number of path comparisons. The key definition here is that a path P is interested in a different path P prime if there is some edge E in P that is interested in some edge E prime in P prime. So now we can state our lemma, and that is that each path P can be interested in at most O of log n other paths. So the scenario you saw before of each edge E in a given path interested in a different path cannot occur. This is of course for the spider graph case, in which we get that each path participates in only order of log n computations, and thus we do not have a lot of congestion. In general trees, the statement is a bit more complicated, and we prove that each path is interested in only polylog n paths of a certain type. The other lemma that we prove is a partitioning lemma. Let us assume for a moment now that we take one of the legs of the spider and make it really long to have, say, linear length. Well, what do we do then? As I said, the complexity will also depend on the length of the paths. And naively, computation on the long path is going to take a linear amount of rounds. This is where our lemma comes into play. We show that one can actually partition both paths into subpaths such that here, for example, you only need to compare the red path to the red path here, the blue path P1 double prime to the blue path P2 double prime, and so on. And because these are disjoint paths, one can actually do it in parallel in the congest model, thus saving a lot of time. Why can we do that? This is because of the monotonicity of min2 respecting cut, which I will discuss in the next slide. But for now, let's focus on a slight caveat here. What if there is no edge between P1 double prime and P2 double prime? How are they going to communicate? For this, we use the routing trick. We show that in this case, it actually suffices to broadcast a small amount of global information in order to solve the case that two paths which we need to compare have no edges between them. Now we discuss a very restricted case of monotonicity just to give you the flavor of what it is. So consider that our tree is just a path and we have some node R, and our goal is to find the min2 respecting cut such that one edge is to the left of R and one edge is to the right of R. So consider that we take some edge E on the left and we find the edge E prime that minimizes the cut value for E of all the edges to the right of R. Well, if this is indeed the minimum, then we are done. And otherwise, one is able to show, as they showed in MN 2020, that the min must happen in one of the following. Either it is achieved by exactly one edge from each red circle, or exactly one edge from each of the blue circles. In this work, we generalize this monotonicity property to turn it into the partitioning lemma. Now we can discuss the algorithm from a bird's eye view. We start with reducing the min cut problem to the min2 respecting cut problem. Then we find the pairs of paths P1, P2 that are interested in one another. Then for each such pair, we compute the minimum cut value over each pair of edges from these paths. And then we output the minimum of the above. So to sum up, we have shown here an algorithm that computes min cut and min2 respecting cut in O of square root of n plus d rounds. Along the way, we proved two new purely combinatorial lemmas about the min cut structure in a graph. The first is the interesting paths lemma, in which we show that not many pairs of paths require a comparison. The second is the partitioning lemma, which basically says that one can apply a divide and conquer approach in order to solve the min cut problem. As open problems, we leave, for example, closing the gap for simple graphs, because there is no tight lower bound for this case. The aforementioned lower bound that I mentioned only works for weighted graphs. What about deterministic algorithms? Well, in our algorithm, both the reduction from min cut to min2 respecting cut and the process of finding the interesting paths are randomized. The best known deterministic algorithm has the following complexity, where lambda here is the edge connectivity of the graph. So of course, in the worst case, this complexity can be very bad. And lastly, a more general open question is to understand distributed exact computations for more problems that for which we understand approximate computation well. For example, single source shortest path, max matching ST min cut, and max flow. Thank you.